Hello all, my name is Yashwant. Today we are going to learn about something on reinforcement learning frameworks and some of the techniques. Once again, welcome back to my sessions on reinforcement learning. In this video, I will break down how RL works, its key components and real life applications, and mainly algorithm used. Whether you are new to the reinforcement learning or brush upping, this will help to build a solid foundations in the reinforcement. So let us get into the slide. So in the previous section, of course, we learned most of the things about reinforcement learning. Let us imagine an agent like a robot or a software interact with its environment. So in this case, agent, it could be a robot or it could be a software. It is going to interact with the environment. The environment could be, for a software, it could be some kind of data which is coming from the user or from a database where the real-time user behavior is captured. Or for a robot, the environment could be its surrounding nature. For any robot or an software, it sees the current state. Based on the current state, a robot or a software chooses an action. So the action could be, for a robot, lifting a bottle. For a software, it could be throwing some particular ad to the end user or end user itself. So if the robot try to lift the bottle or a cup, it might success, it may not success as well. If it is not success, the bottle could be fall down. So in that case, it's a negative remark or a negative reward for the robot itself. It's a punishment kind of things. So somehow the robot came to know that it's unable to do its task. So it also receives some kind of a feedback. It could be punishment, like that. For example, if it is a software, for example, the software as a reinforcement learning algorithm that's running behind the server, throw an ad to the end user, the user which is browsing something, and it randomly throw an ad. It is waiting whether the user is going to click on those ad or not. If the user click on that ad, the algorithm and RL algorithms get a reward point. It might be a very good reward point. It might be slow reward, lower medium range reward point. So every time when an action is happened, there could be chance that a software or a robot might get a reward or it may not get a reward. There are two possibility cases. There could be an immediate reward. There could be a reward which is going to be received after a multiple number of action given to the environment. So based on this action, the robot or in software, it moves to the next state based on what reward it was received from the previous state. The idea is the robot or in software try to maximize its reward point over the period of time. So we try to maximize the cumulative rewards. There are different algorithms used, especially Markov decision process, one of which helps the robot or in the software to learn step-by-step decisions. So for example, if you considered just as an example, so let us consider a machine is playing a chess. If the machine is playing a chess, for each movement in the chess, there won't be a reward. Sometimes we move the soldiers in one direction and we start moving the king or the queen of those in a different direction. So until we complete the chess, the reward could be positive, whether the machine wins the chess or the opposite person wins the chess. So the reward assigned to the robot or a machine will be at the end of the completion of chess game. In that case, the machine does not know that for each step or a changing the each position of the soldier or some other coin, it may not receive any reward from the environment. So the machine, it's tried to maximize its probability of winning the chess by deciding whether if I move this soldier in particular direction, what could be the probability of winning this game. For example, when the soldier at particular position X, the probability of winning the chess for the machine, it could be 0.5. If it is moved in the moves in the diagonal to the right side, for example, the probability could be get reduced. So it might move in the right direction of the diagonal side. The probability of winning the chess could be 0.7. In that case, the soldier movement is decided by the machine. So sometimes the machine could decide whether should I go in the left direction or whether I go in the right direction of the chessboard. What could be the chance? It all depends upon how the robot movements, right? Let me explain in a different way. Let us consider we have some kind of chessboard here. For example, we have a soldier here. If you see, if the soldier is moved in this direction or this position, probability of winning the chess could be 0.3. If the soldier is moved in this direction, the probability of winning the chess is 0.7. At this point, the probability is 0.5. So in this case, if you considered, of course, the machine will select this position, right? 0.7 probability. So of course, the soldier will come at this position. When it comes at this position, of course, I have a probability of 0.7. Definitely, I'm going to win the chance of winning the chess. So in this case, it will try to increase is probability here. For example, it could be previously it could be 0.5, it could be now 0.6. So that means whenever there is a robot in this position, if we see that probability is 0.7 winning the chance, it's try to increase this to 0.6. That means this path making the robot to winning chance compared to this path. For example, if the robot moves at this position, it came to know the probability of winning is 0.6. So there is 0.3. In that case, it tried to reduce this 0.3 to 0.2 because it came to know that the probability is very less at this position. So what we observed is, so every time whenever the robot interact with the chessboard, it's trying to capture its position probability and try to update its previous time t. For example, this is t, if this is t plus 1, whenever robot at this position, we try to update this one based on the current position of probability. So that means this is what we call as a temporal difference technique. So the idea is, sometimes you might ask, right? For example, if you see whether we might always choose this path because the probability is 0.7. From this path to go to this path, in this place it could be 0.9 in this box, in both box. So if you see the path is going like this, so there could be chance sometimes a robot will choose this path 0.3 and try to update the previous state, this state, into 0.2 case probability 0.2. In this case, what robot is doing here is it tried to see, is there any possibilities or in state it can move and try to reach us to the winning state. So that means the previous section I mentioned 2 points, that is exploration and exploitation. So in this case, the robot is trying to explore the new possibility state by considering, even though 0.3 as the probability of winning, and try to maximize his reward point in this direction to achieve his goal. If it is already know what is the direction from a soldier can move, that means a machine just shift this position to this one and try to move this one and try to make a winning state. So that means there are algorithms utilize these techniques to achieve the goal of the agent, whether it is exploring new possible path or a new possible state with the getting the trial and error and to reach the success, or if you already know that this is the path, if I go there like this, I can ready to achieve this one. There are 2 type of possibility how we can utilize this. I will give you another simple real world example. Let us consider, if you are in London, you already been in London last month, you went to a particular restaurant, you already know what is the path to go to the restaurant. If you already explore that, you will directly following exploiting. It does not go to another exploration, the new path. So if you want to explore new restaurant, it might take some time, extra time. You will go to different street, and if you try to find a restaurant. If you does not get, you will try to figure out something new in your own direction. So finally you want to achieve, you want to reach the destination of a good restaurant. So once you reach there, after exploring multiple paths or multiple street in the London street, you will come up with a good restaurant. When you are being in a London the last week or last month, you already explored one restaurant A, and this week you will explore B. So you already know this two restaurant are a success where you can reach or a goal with two different directions. So you already captured this information in an agent. What we learned. Sometimes if you take another exploration technique, you may not reach us to the desired destination or a restaurant. You might come back to your previous state and start looking for the best state which you already explored. So there are different approaches how to find the best reward points to maximize your current rewards. So get into the next slide. So here if you see, it's a block diagram of reinforcement system. We have an agent here. For the agent, the input could be reward or it could be punishment, and you will give the output could be an action to an environment. So how we are going to be, who is going to be evaluated? Something, an error has to be captured here, right? In order to the agent supposed to be learned. So the evaluation is coming from the environment itself. So if you see in our machine learning or in a cluster part, especially in the non-supervised machine learning technique, we have an error. For example, if you take in supervised, what we will have? For example, this is the input, and for example, this is the input, and this is agent or an ML, and this is an output, right? But of course, at this time, this is your target. This is your error. So you give an input. It is in the supervised machine learning, we are going to produce the algorithm, or a machine learning algorithm is going to produce an output. The output, whether the output is correct or wrong, we can evaluate using our target, which is labeled earlier. Based on this, error is going to be captured or calculated, and it is back propagated in the any ML approach, any algorithm, and try to minimize this error using some kind of gradient descent or some other algorithm. Try to minimize the parameters of an ML algorithms, and try to make this output error is equal to 0. This is our target. But in reinforcement learning, as I already mentioned, this is the agent, this is an output, this is an input, this is an environment. So agent is going to learn with trial and error technique, with input as an reward and punishment or penalty. So this is the quite difference if you see RL how ML works. So in this block diagram, this is a simple block diagram to show how reinforcement learning works. The agent decide what to do an action. That action affects the environment. The environment gets a feedback. It could be a reward and the new state as well. The agent then uses this state information to make the better decision for the next time. If it is getting reward means it is happy with that action. If it is getting punishment means it is not happy. It understands that whatever it did, it's not correct. This loop continues until the agent learns the best way to behave in the environment to achieve its goal. So there are different applications currently used in as I already mentioned, in robotics, especially for the navigation and locomotions. In robotics, robot try to learn to walk, grasp, or even fly as well. And when it comes to the gaming, the AlphaGo and the OpenAI 5-bit word class players uses reinforcement learning, especially in the field of healthcare as well, where adaptive treatment based on patient feedbacks. And as of in finance, a smart trading system try to optimize the portfolios, and especially in the smart grid as well, managing electricity demand in the real time. Especially reinforcement learning is used to shape the future in this type of industries. So if you see the real world examples, it depends how we are going to address the problem statement. So reinforcement learning is needed where an human currently doing can be replaceable with this type of algorithms. For example, as I already mentioned, I gave an example. If the software is running at the behind, I want to suggest some subscription features to the end user. For a particular user is using our software for the many days, but he is not subscribing to the paid features. Our reinforcement learning can try to understand the user activity. Based on the user activity, our algorithm can suggest in a real time or in non-real time for a particular subscription. The user might take the subscription. If it is take the subscription means, of course, I will get a reward point of 3. For example, it is scalar value plus 3 I will receive. If the user click on the subscription and he subscribed, then I will get a reward points of plus 5. So this success, if I reach success rate, then I will get more reward points. If I reach intermediate, so let us reward point is plus 3. So it's a kind of scalar value I am going to receive based on the user activity. If the user not click on the particular subscription ad, in that case, I will make -1 or -2 as the punishment for myself or a penalty on my state, and I'll try to understand. For example, when I was trying to give an ad to the subscription for a user based on his activity, when I get subscription, plus 5 as a reward, then I understand that whatever activity which I seen, those are all, I will try to increase those activities with the probability of subscription to higher probability. If I get a negative reward, punishment, then I mark those activity to lower probability of subscription. User might choose the subscription. So these are some of the real world example how we can use the reinforcement learning at the back end to do, instead of human, our algorithms or reinforcement techniques or agent can do the job. So in the previous case, I explained in one of the chess case how the probability of winning the chess might be changes, and try to update our previous state based on the current state of probability of winning the chess. So this is what we call as a temporal difference learning. So the agent actually learn from the experience. Temporal difference learning is a popular method. It combines two ideas. For example, sometimes learning from the complete episodes, or if you complete all the chess game, you are able to get a reward point. So that's what we call as a learning from the complete episodes. So this type of method, what we call as a Monte Carlo methods. And there could be another approach called what we call as a dynamic proning, learning from estimates. Each step by step. For example, if I do some type of pedaling a cycle, of course, I'm able to balance and try to move. So my father gave a pad on my shoulder, so that's a positive reward, and immediately I got an, for example, or he claps, I'll get a reward points. So let us consider, if I ran this, I try to pedal the cycle, I go over the stone or some obstacle, and then I try to balance the cycle for a few seconds. I was unable to balance it and fell down. So the reward point is a punishment. In that case, it's not for the previous action or the state. When I was trying to balance the cycle, I'm getting reward as a punishment. No, that's wrong. So balancing is not causing the fell down, right? The punishment or fell down, it's coming from the previous, before the balancing, when you try to cycling on the obstacle or a big stone, that causes this punishment. So that is what called temporal difference. In that case, we want to go to the previous state of that particular state and try to reduce the probability of pedaling or balancing to a lower number from the current state. There are, for example, as I mentioned, learning from the complete episode. It could be chess. The previous example, I gave some different approach to, for each steps, I'm going to capture the reward point. In the chess point, where we try to complete the chess and try to get the final results, whether it's reward or punishment, like that. So we try to use dynamic programming, learning from the estimates. In temporal difference, the agent learns from each steps using bootstrapping. Some of the examples like TD01, SARSA, or Q learning. This helps the agent to learn faster and adapt to the environment. So there are different algorithms. Like let us quickly go through this main type of algorithms, like a value-based algorithms and this learns the value of the actions like Q learning or a deep Q learning. And also we have a policy based algorithms and Actor-Critic and a model based algorithms. And where it comes to the Actor-Critic, a mixture of both approaches, one part chosen actions and other from the evaluation them. Model based, this builds a model for the environment, especially to simulate and plan the action ahead. Each type has its own strategy and useful for the different scenarios. So these are the different key RL algorithms. In the upcoming session, I'm going to explain in details for which an examples and the real world use cases, and try to go through each step by step in a programmatical way. This is all about from reinforcement learning frameworks and some of the algorithm side. Thank you so much. Bye.